Hello and welcome to homework 4 part C for process dynamics and controls. And in this part we have four things on our agenda. First, we have to explain the principle of the bode frequency stability analysis from the practical viewpoint of microphone/speakers feedback and why the amplitude ratio of 100-degree phase lag is relevant. Then we'll also algebraically show how the substitution of S equals JW into the open loop transfer function yields amplitude ratio and phase lag in a bode frequency response analysis. 3. We will simulate the response for a first order in a sine input, explain the early time behavior, and compare the magnitude ratio with that obtained from a bode analysis. And then finally, we will derive the analytical expression for the amplitude ratio divided by phase lag for a first order system with a proportional only control, and also that of a pure dead time system. So without further ado, all of the work today I think will be on the iPad, so let's get into it. So as always, we will write out our diagram, homework 4B. We want to imagine that there is a person here singing into this little microphone. And there is a cord that goes to a big boombox stereo right over here. So obviously this is the input, output. And so for this system, we are going to say that the phase log is equal to that. And when it's greater than 180 degrees, our amp ratio is greater than 1, and the inverse is true. And then you'll also have kind of all right. So for part 2 here, we are going to actually draw another diagram, and that is going to be an arrow saying going here. This is YSP, and it is going to be going into the system that we will call GC. Another arrow going into another system, this GP. Okay. Arrow out, arrow down, into another system we will call GM. And then dots there. Bang. All right, so let's get into the algebra. So as I said, we now have quite a bit of algebra to do. The first thing we want to say is that G equals the product of TF. Now, first equation is quite a long one, so you're going to say that G is equal to, not equal to, multiplied by W over S squared T W squared. Now this is going to be equal to A1 over S plus B1 plus A2 plus S plus B2 all the way to CS plus D over S squared plus W squared. Now what you want to do now is multiply both sides by S squared plus W squared. And what's going to happen is this is going to cancel, this will cancel, and this will cancel. And you now have a new equation of GW equals A1 times S squared plus W squared over S plus B1 plus A2 multiplied by S squared plus W squared over S plus B2 CS plus D. And now again, you can cancel out both of these terms and you get the equation A GW equals CJW plus D. And for this one, if you remember from the problem statement, we were able to get this because we set s equal to jw and j equals square root of negative I. Now from here, we're going to let g equal kck over tau s plus 1. And when you plug this back into the equation, you get AW times KC times K over tau JW plus 1 equals CJW plus D times 1 minus tau JW, and this is the conjugate. So now what we want to do is multiply by both of these by 1 over tau JW. I'm sorry, actually divide this. So this will cancel out this, and you will be dividing over here. You will arrive at AW brackets in the numerator. You have KCK times that 1 minus tau JW that we just multiplied by over 1 plus tau squared W squared, all equal to CJW plus D. And then again, you can separate out this into AW times KCK over 1 plus tau squared W squared. And you want to separate the real from imaginary because, as we said up in here, J is equal to negative imaginary I plus negative J times KCK tau W over 1 plus tau squared W squared, again equal to CJW plus D. I'm going to label this as real and imaginary. Go to the next page. And we're going to want to, this R value is equal to all of this, and I will be equal to all of that. And when rewritten, and so now that we know what R equals and I equals, we are going to say that C is equal to A times I, our imaginary, and then D is going to be equal to A times W times R, which is our real value. And now, when you rewrite this, AI times S over S squared plus W squared plus AR times W over S squared plus W squared, you see that this value and this value, both, this is cosine and this is sine. So again, we're able to rewrite this and get AI cosine of W cosine of WT plus AR sine WT. And then you can multiply A by all of this, so I cosine WT plus R sine WT. Now, next step of this is we're going to let H equal WT. So sine H plus H equals, sorry, this is K, equals sine H times sine K plus sine K cosine H. Okay? And now finally we can rewrite this again. This is so much algebra. A times sine of H plus our original value equals A hat sine H cosine plus sine cosine H. And so I was looking ahead into just kind of planning what I'm going to have to do next. And I don't know why I said we're going to be only on the iPad. This is definitely going to have some collab in it. I'm sorry, I misunderstood. But anyway, this is going to be our real term, and this is going to be our imaginary term. And so you have r equal to a hat cosine, and then you have I equal to a hat sine. So next, r squared plus I squared is going to equal a hat times negative cosine plus sine squared. Bang! So now you have a hat is equal to radical I squared plus r squared. And this is the equation that we have been looking for. And you cannot forget to mention that I over r is equal to sine theta over cosine, which is equal to arctan. So now we will get into color. So as you can see, I am uploading the library right now, so we are able to run this. And the first thing that we're going to do is actually look at the sine function on a graph and analyze the oscillations. Our kc value, 1, our k value is going to be, hate when it does that. Don't want as integer. It's 1, k is going to be 1. Oh my gosh, that's really frustrating. Tau is going to be equal to 20. Our w value is going to be equal to 0.1. And our g value is going to be equal to kc times k divided by tau times s plus 1. Then we need to add another line of code, and that would be t and h are equal to sim of g lambda t 2 times np sine of w times t other n equals 1000 dt equals 0.5. And then we can add another line of code, and that is fig equals underscore subplots fig math underscore scatter x equals t, y equals h. Mode, it's going to be equal to lines. On this, so as you can see, we have our sine function here. The first spike goes a little bit above 1, and then you can see it kind of goes down into its natural pattern of oscillating between about positive 0.08 and negative 0.88 and negative 0.88. So you can see this is kind of steady, but then we also need to look at the Bode analysis. And so to do this, we're going to look at, plot this magnitude and angle. So we're going to add the next line of code. We're going to do fig magnitude angle equals Bode of g. Run this. And so you can see this top line, the magnitude, is magnitude of 1, and then it's kind of just a linear drop here, whereas this angle more so is more gradual, more of like a slide shape. And so now we are going to go back onto the iPad. So we're going to start with this new equation for the last part of this problem, which is g is equal to ke to the power of negative s theta over our tau s plus 1 value. Now, if you remember, s we know is jw, and j is equal to square root of negative 1, which is an imaginary number. So you can rewrite this again to ke equals negative theta jw over tau s plus 1. And we're going to say that e to the power of theta wj is equal to cosine of W theta minus imaginary number of sine W theta. This is our real, this is our imaginary. So now when rewritten, a hat is going to be equal to, as we said, I squared plus R squared, which now equals cosine squared W theta minus sine squared W theta. This will equal 1. And now do remember that this is going to be the arc tan of I over R. And so if it's equal to that, it's also equal to arctan of sine over cosine, which equals W theta. So we will highlight these. I realize you can't even see those, so let me zoom out here. There you go. 1 and W theta. So now, the last part is to work through a couple more equations, in which, if you remember, our value, our real value, is kck over 1 plus tau squared W squared, and then our imaginary is equal to negative tau W over 1 plus tau squared W squared. And so what we're going to do is plug this into the equation right there to get a hat is equal to kck times 1 plus tau squared W squared over 1 plus tau squared W squared, which then equals kck over 1 half 1 plus tau squared W squared, which we will highlight this. And then finally, you arrive at this equaling arctangent of negative tau W. So, I'll zoom out and highlight this. Here we go. And just so you guys remember, as a reminder, this was us explaining the principle of the mode frequency and stability analysis from a fractal viewpoint, and why the amplitude ratio at 180 has the phase lag and why it's relevant. We then algebraically showed the substitution of S equals JW. We simulated it in Colab, and we finally derived the analytical expression for this. So thank you for following along. I hope this was helpful.